So, in my last class I talked about quantization of electromagnetic field in vacuum, in the sense that you do not have any source or sink, neither any charge distribution nor any current density. And then we have seen that electromagnetic field, quantized electromagnetic field in vacuum can be considered as a bunch of one dimensional quantum harmonic oscillators which are non interacting, and these harmonic oscillators are specified by the frequency as well as the polarization. Okay. Right. So, the question is that what should be the possible states of such a quantized electromagnetic field. Okay. So, what we discussed last time is that if I look at the energy of this quantized electromagnetic field, that means I consider a vacuum, I mean some cube with conducting surfaces, and inside it is vacuum. Then inside that box, in that cube, the total energy, if I quantize it, it consists of all the harmonic oscillator energies, right. So, this is k as well as s. K is the wave vector and s is the polarization, h of k and s, right. So, each k, each of these Hamiltonian corresponds to one dimensional quantum harmonic oscillator, right, with frequency omega k, which is c times k. K is the magnitude of the wave vector. So, now if I look at what are the eigenstates of these Hamiltonian, that means the quantized electromagnetic field in vacuum. So, the eigenstates in the simplest term will be the eigenstates. So, if I call this eigenstate as say n, okay, for this thing, let us say it is k and s, right. Then this will be basically for. So, let me enumerate them. Let us say I call it as k 1 s 1, this is first mode, then second mode k 2 s 2, this corresponds to the polarization 2 degrees of freedom, so on and so forth. Then the eigenstate of this H, the product eigenstates will be something like this: k 1 s 1, tensor product n k 2 s 2, so on and so forth, right. Okay. There will be degeneracy, but this is common eigenstates. I mean these can take values from 0 to infinity, 0, 1, 2, etc. So, in principle, when I say that we have n photon state means for this quantized electromagnetic field, it means that this state. So, this n k 1 s 1 plus n k 2 s 2 plus so on, this is my n. Okay. So, this is the total number of photons. So, here I am considering all the modes, but if I want to restrict myself to individual mode, that also I can do. So, I will choose for example, this one. Okay. So, this corresponds to a single mode.
K indicates the momentum of the photon, but
Moment S is the polarization, 2 degrees of freedom. Yes. Okay. So, now so this is the the product basis, but there are interesting states which are not eigenstates, interesting states of. So, let me concentrate on single mode, later on we will consider multi mode case also. So, some of the interesting states of quantized electromagnetic fields, single mode quantized electromagnetic fields are like coherent states, which you denote by alpha. This is single mode, I am talking about now single mode system, and this is the alpha is a complex number. In terms of the eigenstates of this individual, I mean the single mode system, Hamiltonian energy eigenstates, this can be written as mod alpha square by 2 into summation 0 to infinity alpha to the power n by square root of n factorial n. So, these are the Fock states, I mean single mode energy eigenstates. Okay. I will talk about it in great details, I mean after some time. So, these are coherent states.
Goes n is what?
0 to infinity. So, n is your energy eigenstates, for harmonic oscillator. No, this is single mode case. I am talking about now single mode. This is all the modes together. Now, I concentrate on single mode. Okay.
So, for one K1 and
one S1, yes, yes.
So, if you have, I think you mean K1 is varying from all possibilities.
No, no. When I say single mode, your K is fixed, S is also fixed.
Then it's a one state. So, what? Why is n running from 0 to infinity?
No, no, no.
All the others are. Oh, okay. In that mode, they are money 1 photon, 2 photon, 3 photon.
0 photon, 1 photon.
Okay.
Sorry?
I was not here in the last.
Uh-huh.
You are discussing only free photon quantization.
Yes, 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 yes. There is some factor depending upon R. This is normalization factor, n is equal to 0 to infinity. This is single mode squeezed vacuum state. Okay. Here R is a non-negative number. This is called squeezing parameter. Okay. Yeah. And also you will have thermal states which is like rho thermal, which will be like the thermal distribution of harmonic oscillator. So, it will be n is equal to 0 to infinity e to the power minus beta h cross omega n plus half divided by sum over m is equal to 0 to infinity e to the power minus beta h cross omega n plus half, okay, then n n. So, this is a mixed state. Okay. So, beta is the inverse temperature and omega is the frequency. Okay. So, there are plenty of other states also. Okay. I will talk about it later. So, therefore, for single mode quantized electromagnetic field, these are some of the states which we will be discussing in details. Okay. Right. Okay. So, let me now concentrate on these coherent states, and because this will be useful to describe this phase space distribution function. So, let me first concentrate on coherent state and then I will come back to this later.
The squeeze state is a state localized at a particular radius.
No, I mean, so basically this is what I will discuss. So, basically when we have a quantized, I mean a state of quantum state of light, okay, I can measure uncertainty in its position, one of the quadrature. I can also measure uncertainty in its momentum, the canonically conjugate quadrature. If I take the product, uncertainty relation tells us it should satisfy the Heisenberg uncertainty relation. coherent state is such that this uncertainty product it minimizes. That means, the product of the uncertainty is the minimum value. Not only that, the individual uncertainties are same. Okay. Squeezing means one uncertainty, maybe it is in the position or in the momentum, can be enlarged a lot, but with the cost of minimize, I mean reducing the uncertainty in the canonically conjugate variable like momentum, I mean very very small. So, that is what squeezing means, but the product will remain again minimum.
And gamma is the parameter that measures how squeezed.
Exactly. Yeah, this is R, but anyway, yeah, this is the parameter how squeezing is it. Yes, yes.
R is not the distance.
R is not distance. No, R is not distance. Okay. Okay, good. So, I'll come to this later. In fact, squeezing can be made even, this need not be real, this can be complex also. Okay. So, let me concentrate on coherent states. Why I am going to concentrate on coherent state? Basically, coherent states are quantum states of course, but they behave very closely to states of classical light, that means classical electromagnetic wave. Okay. And that makes our life much easier. Okay. So, let me talk about first some properties of coherent states and then I will come back to other things. Okay. So, number one is that if I take two coherent states and take their overlap alpha and beta, these are complex numbers, right. So, if I look at this formula, this will be exponential of minus half mod alpha square plus mod beta square, and then there will be, there is some term like plus alpha star beta. Is that correct? If I take this formula, these are the orthogonal states. So, this is the things. So, this will be exponential of minus half alpha minus beta whole square, and then what will be this? There will be some phase factor. What will be that phase factor? So, this is mod alpha square mod beta square exponential of, whether it is plus I iota or minus iota. Can you confirm me? Imaginary part of alpha beta star, whether it is plus iota or minus iota, it should be so. This is alpha beta star, alpha beta star. So, plus of, yeah, this is a half alpha beta star. I think this is correct. Okay. So, just my question is whether this will be plus or minus. I think it is plus. Okay. Anyway, this is simple matter, you can verify. So, this you see that for any two coherent states, they are not orthogonal. Okay. So, if I want to make alpha beta magnitude to be much less than 1, that means close to 0, this is equivalent to saying that alpha minus beta is much greater than 1, right. So, that means the 2 points in the complex plane must be very far apart in order that they are almost orthogonal, right. Okay, good. How many coherent states are there? So, if I look at the collection of these coherent states where alpha is a complex number, this is infinite set, in fact uncountable set, right. But what is my system? What is the dimension of my system? This is quantum harmonic oscillator. So, countably infinite, right. So, therefore, what can I say about the linear dependence or independence of these coherent states? Dependent?
Linearly dependent, of course.
Linearly dependent? What does it mean?
We have over
combinations of these alphas which give you 0.
So, does it mean that if I take, let us say, sum over some alpha, I do not know, f alpha, this is coefficient, and then alpha, this should be 0 for non-zero f alphas, right?
Some non-zero.
Some non-zero, yeah, not all of them 0, but how many such alphas I should consider? Is it the entire complex plane or some part of it? What?
I think the circle is
Circle, okay. Why should I take circle? I can take something else also, right?
for any given alpha and beta, the dot product will never be 0, right?
Yes. If alpha and beta are different. Yes. So, if I give you an infinite set of vectors, these are infinite set of vectors, right? What would be the characterization of their linear independence? For finite set we know, but if I give you infinite set of vectors, what would be their characterization for their linear independence? Independence or dependence, whatever you want to call. For infinite set of vectors, how does one characterize whether the set is linearly independent or dependent? How do you check whether the set of vectors is linearly independent?
Maybe if you want to replace it by an integral, like if it's continuous.
Yes, but how will you do it practically that that it is linearly independent or dependent? Integral of course you can do, but that requires the entire set. Okay.
So linear independence requires us to satisfy that criteria that alpha
Yes,
conjugation
yes,
is
but that the main question is how many alphas I should take?
Consider two different alphas and project it.
Project it means what?
Then, like if you get corresponding coefficient for both the projectors, they are like all dot.
Well, why should I take only 2? I can take 3 also, 4 also. Where is the problem?
So, what is the question? How do you
Question
characterize linear
is for
dependence?
infinite set. This is infinite set, right? How will you characterize linear independence of such a set?
Sir, so for any finite alpha and beta, they will
Hmm.
never be orthogonal.
Yes.
So this means, I mean, we want to find the linearly independent set, but we can't even find two orthogonal. So, I mean, for two alpha and beta to be orthogonal, they have to be two complex numbers with
The
difference.
linear independence does not necessarily mean that they need to be orthogonal. Right?
Yes.
So you pick any arbitrary countable basis out of this, and then you produce another state which is not a combination of all that basis. Then you can show that you can do it for every such countable basis, but you never exhaust all possibilities. That will give you characterization.
Okay, but practically even you cannot deal with countable infinite set, right?
Yeah, and you say, okay, this is an uncountably large set, we agree on that. You pick a countable set out of it, arbitrarily, and then you show that, okay, there exists another vector which is not a combination of this.
So therefore, this is basically that countable set subset is linearly independent. That's
Yes. Okay, that will characterize linear independence. Yes.
right.
Yes.
So therefore, for an infinite set, how will I characterize its linear independence? Basically, I choose an arbitrary finite collection and show its linear independence. Otherwise, how will you do it practically? It is impossible. This of course holds good for finite collection of sets also,
It
vectors.
will exhaust.
So, what is, so how will I check linear independence of such an infinite set? I choose arbitrary finite collection of states from here and show its linear independence. If I can manage to show that, then of course, this set itself is linearly independent. Okay? Is that clear?
But can you have more than two such linearly independent states?
More than two such means?
As in you said that we have to find a collection of finite sets.
Any finite collection.
Yeah, will they have more than two elements?
Well, if you take singleton set, then it does not make any sense for linear independence.
Yeah, like
Yeah, you can have more than. Where is the problem?
I take ket 0 and one where alpha equal to 0 and another at ket alpha equal to infinity, and I think that kind of exhausts maybe.
Exhaust means what? No, no. For linear independence, you will have to show it for arbitrary finite subcollection of it.
Okay.
Okay. For linear dependence, there is no issue. You can choose any one and show that this is linearly dependent. But for linear independence, you will have to choose for arbitrary subcollection and show that this is linearly independent. Okay. So, my point is, if I choose a collection which is like alpha 1, alpha 2, alpha m. M can be anything, you know, it can be any finite number. Only thing is these are different. These are different complex numbers. Then you can show that they are linearly independent.
For any
Any chosen. Only thing is they should be different, because you know if you choose one of them, two of them same, they are no more linearly independent. Okay. So, what you can prove from this expression is that if I choose any such finite collection of different coherent states, they are bound to be linearly independent.
So, can I write any state of this system in terms of alpha and beta? Alphas are imaginary numbers.
Yeah, complex numbers.
Complex numbers.
Yes.
Yeah. So, integer plus n plus im, where nm are integers.
Yeah.
So,
Why not?
Can I write any state
Hmm.
in terms of this set of states?
Integer, no.
I need more states also.
Yes. Yes. Yes.
So, what is the complete basis in this case? For example, harmonic oscillator, we know the complete basis 0, 1, 2, 3, 4, 5, 6.
Yes.
But
This is also complete basis, but only thing is this is not orthonormal basis.
yeah, but I mean, we don't know the complete basis here.
I'll do that. I'll do that. So, for the time being, this is what. So, this I am not going to prove it, but you can argue yourself that if I choose this alpha 1, alpha 2, alpha m to be different from each other, then they form a linearly independent set of coherent states, and that tells you that this set of coherent state is itself linearly independent by definition. Okay. So, this is a bit tricky issue. We are dealing with uncountable set and talking about linear independence, but the point is for uncountable set linear independence comes in this way. Okay, good. So, next thing is that so, now let us take projection on these coherent states and add them all. So, because this is complex number, I will have to take. So, d square alpha means this is the real part d of real part of alpha times d of imaginary part of alpha, okay, because this is complex number. And for normalization, this is the standard one. So, alpha belonging to complex plane. So, I integrate it. Okay. So, then this is important, this 1 upon pi factor for normalization. Now, I have erased that part alpha. So, let me alpha, what will be that? Alpha to the power n, alpha star to the power m, n factorial, m factorial. This is n and m, right? Is that okay? Right. And now you can choose, for example, alpha is equal to r e to the power I theta, and then do all these things. Okay. There will be, basically this you can replace by r is equal to 0 to infinity, theta is equal to 0 to 2 pi r d theta dr, right? Okay. And then, if you follow all this, what you will get ultimately is sum over n is equal to 0 to infinity n n, right. I hope you can do this is simple integration, So, there will be this integral like this, theta is equal to 0 to 2 pi e to the power I n minus m theta d theta. So, this is what will be the value of this? Right? Yeah. So, this is what you need to look at. Now, what is this? This is your identity operator on the entire Hilbert space, right. So, you see that coherent states, they form a complete basis, is not it, right, because if you take projections and sum over all those projections on coherent state, it gives rise to identity. So, these three properties tells you that this 1 plus 2 plus 3, these three together tell you that these coherent states, they form an over complete basis. Basis, of course, because of this, over complete because you are your Fock space is countable in infinity, but this is uncountable set. Okay. Good.
But if we take any alpha,
yes,
and remove it from the set,
yes,
of possible vectors, then can we write any state in terms of the other vectors?
yeah. So, this is okay, it depends, because 1 alpha does not make sense. Okay. So, what you are asking is, okay, I want to write a state of my quantized electromagnetic field as, let us say, alpha belonging to C d square alpha or whatever, then what you want to write is, so this is C minus, let us say, beta. Okay, I am taking out this thing. So, this will be something like psi alpha, then alpha, this is the coefficient, right. This is what you want to write. Okay, good. Well, there will be, in general, it is not true,
Not possible to write.
not possible. Okay. There will be some error, but because this is continuum, the error will be very less, but still it is not possible. Okay. So, this is, I mean, bit tricky issue. So, you cannot even take out one particular point.
That depends on the measure.
Of course,
The way
but
you're
there will be,
defining-
but this is I am talking about exact case.
Yeah, so what I'm saying is that here you have defined the measure as like dx dy
Yes,
in the complex form. Had I chosen to work with a different measure,
of course.
then I can.
Yeah.
it-
This is
removing
this
one
is
part
all
doesn't matter, right?
uniform measure, hard measure, whatever you want to call it. Yes. Yeah. Okay. So now, once we have this result, that this is an over complete basis. So, I choose any density matrix of, so I suppose all of you know what is a density matrix, right. So, I choose any, so density matrix you can think of as a mixture of projections on pure states. Okay. So, you choose any density matrix of my quantized electromagnetic field single mode, I can write it as this is simply identity operator, this is rho, another identity operator. I can always do that, right. So, this can be written as 1 upon pi square alpha beta belonging to C d square alpha d square beta. I mean, when I write this means this is of course double integral, I am not, well, if you want you can put here also. Okay. So, then this is alpha rho beta and then alpha beta, right. So, basically you are writing rho in the coherent state basis, this is not even countable basis, fine, there is no, I mean nothing spectacular about it. Here comes the great works of Glauber and Sudarshan, who have done it independently. They said that no, you do not need all this. What you can write for any such state, which is called as diagonal representation. So, you can write it so, this is a real valued function depending upon rho, and I am writing alpha and alpha star because these are two independent complex numbers, right. So, you see that you do not need these two indices alpha and beta, just one is enough. So, this is what is known as diagonal representation or Glauber Sudarshan P representation. So, this is this function, this is called as P distribution function. So, I will of course, I mean this is very important for continuous variable system, particularly for quantum optics. I will discuss it in details how does one derive this. But for the time being, you see that any state does not matter what it is of quantized electromagnetic field single mode, you can, I mean this can be extended for multi-mode case also. So, you have only one index, right, everything can be written. Okay. So, this is so powerful, I mean I do not want to go into the the controversy of Nobel Prize etc., but this is so powerful result. Okay. I will do that, not now, but I will do that, yes. So, the question is that why is it so important? I will discuss after some time that this coherent state, these are coherent states. Coherent states are, they behave very closely like classical light, states of classical light, okay, which are called classical coherent light. Okay. So, you see that any state of your quantized electromagnetic field, quantized radiation field can be written as a linear superposition of projections on coherent states, and these are classical like states, right. So, as a whole this will be classical state, this will behave like a classical electromagnetic wave state if I can show that these coefficients they form a probability distribution, that means they are non negative and add up to 1. then this will be basically mixture of classical like states, and therefore, this will also behave like a classical state. That means, something similar to classical electromagnetic wave, right. Thermal state is one such example. Okay. So, the light which comes from here, unpolarized light, of course, I am not talking about any polarization here. I mean, you can specify polarization, but this is thermal state is one such example. Okay. If I look at a coherent state itself, so if I take rho as say which is a projection on a coherent state, then you can figure out what will be this one.
Beta. P beta beta.
So, what will be P beta?
Delta function on this.
Yes, this is the delta function alpha minus beta, right. Okay. This is two dimensional delta function, yes, or complex delta function, whatever you want to call. So, this you see for a coherent state, the P distribution is itself not a proper function, it is a generalized function, and we will see that if I take like Fock states like K1, K2 etc., then their corresponding P distribution will be derivatives of this function. So, these are very very badly behaved functions. Okay. So, this highly singular function basically.
I'm still not able to wrap around the maths part, but
No, this I will
physical
prove,
motivation-
this I will prove,
No,
this I will
I
prove.
mean, simply speaking, what you are doing is a diagonalization of a very complicated matrix.
Exactly.
But that's not always simply done, right? Okay, let's forget about it. But what is the physics motivation for like going from the second equality to the third equality? What
From
is the
here to
basic-
here?
Yeah.
Yeah. So, the physics comes from the fact that basically the coherent states, this I will discuss also. Coherent states are very closely related. These are the closest quantum states to classical light, okay, states of classical light.
One alpha represents one particular mode. Of
This is
the
mode, I mean these are all single mode, these are all single mode. So, one such alpha corresponds to a state very close to a state of classical electromagnetic field, that means classical light. Okay.
And what can you give an example like what alpha corresponds to? What classical light state?
Yeah. So, this alpha basically it will, so alpha I can write as its real and imaginary part, right. So, generally I can write alpha is equal to x plus I p by root 2, x is x by root 2 is the real part and p by root 2 is the imaginary part. This x and p, these are called quadratures, okay, amplitude and phase quadratures for the classical light. Okay. So, classical light, these quadratures will, and this is what I will tell you that how they come in the classical electromagnetic wave, and basically specifying alpha means specifying these quadratures.
So basically, the classical light that you are speaking about is the light with amplitude x and phase p.
Yes, but I mean yes, that is true, amplitude. I mean this is, one should call it as the, I mean the average quadrature with respect to alpha is this x, average quadrature with respect to, I mean the amplitude quadrature, and average phase quadrature with respect to alpha is p. So, basically it means that if I fix this x and p for a classical light, that I can always do, okay, then so let us say this is my x and p. Okay. So, if I fix a point here which corresponds to x and p, so these are the values. So, the corresponding coherent states will be basically you draw a circle with center as this, okay, right, and so this is your delta x square with respect to this alpha, and this is your delta p, I mean these are the operators, okay, square with respect to alpha. Okay. So, if I fix this point which corresponds to this x and p quadratures, amplitude and phase quadrature of classical light, then corresponding coherent state will not be actually this point, but this uncertainty circle or uncertainty area.
The average over all
Yes,
the
yes, yes, yes.
no, the classical light state.
It's not, I mean,
Classical mixture of these.
classical light corresponds to this x and p, okay? This x and p fixed value. Corresponding coherent state means this uncertainty area, okay? Right. So, and there can't be any other quantum state whose uncertainty is less than this area. This is why we say that this is the closest state, quantum state corresponding to this classical state of light.
And now rho was an arbitrary state of the light,
Arbitrary state of the light.
and you did a decomposition in terms of the small circle.
Yes, yes, yes.
But then you say that somehow it's localized on a band. This diagonalization is basically a band, like it's on the
Yeah. So,
45-degree line.
I mean, for a generic state, this is for coherent state. For a generic state, this uncertainty will not be like this. It will be straight over.
Correct. But then this representation, alpha alpha diagonal representation, is basically you are localizing around the band of the 45-degree line, right?
Yes. Right. Yes.
So
Yes.
that's
Yes. I mean, okay. So this is actually, this is very non-trivial to come from here to here.
yeah,
Okay. So this I'll of course do that.
yeah.
But why coherent state basis? That is what I want to motivate us.
But that I understood. But then diagonalization.
Yeah. So this is quite non-trivial. I'll do that because this, if I want to do it now, it will be too much for me. Okay. So I'll do that later. Yeah. But this is quite non-trivial. And more important thing is, you can't have any other basis through which you can have a diagonal representation. Okay.
And do we know the reason for that?
Yeah. So this is all this depends upon basically the uncertainty. Okay. So for example, let me tell you squeeze states. So identity, this we have seen that this is 1 upon pi alpha belonging to C, d square alpha alpha, right? This we have seen. Now squeezing is a unitary transformation S of R, which is I think this is exponential of R times A square minus A dagger square, something like this, okay, real squeezing. This is a unitary operator. Now, if I apply the squeezing on my vacuum state, what I will get is this R, which I have written, a squeeze, 2 more squeeze vacuum state, not 2 more, single mode squeeze vacuum state. Okay. So, now this is unitary. So, I can apply this unitary here on both sides, right. So, this is S of R and S of R dagger. This will still remain identity. So, what is this? This you can say that squeeze coherent states. You are squeezing coherent state, that is also valid state, right. Its the phase space distribution will also be Gaussian or whatever. But the problem is that now, and this will form a basis, right, because if I choose different alphas, they will be linearly independent, all those properties will be there. This will form a basis. This is of course true, this will form a basis. Now, can I write this rho in a diagonal form with respect to these bases, if I ask that question? Here I have written in terms of coherent state basis. I can also try to write it in terms of these bases. where is big deal with this? I mean this of course I can write, okay. But can I have a diagonal representation? Answer is no. Okay. So, and why this is no? It is so basically the point is that in the coherent state you have the minimal uncertainty of the quadrature variables. In all other states such minimum uncertainty is not there. Okay. Okay. Yes, so I understand that this jump is is an abrupt jump, but I'll do this derivation. Okay.
So this P alpha comma alpha star, you said whenever this is positive, it corresponds to a classical state.
Yes.
So
Yes. Because it is classical in the sense that is because this is just classical mixture of classical like states.
So if P alpha comma alpha star is delta function as you mentioned there, then the coherent state is itself
is a classical state.
it's a classical state.
Yes. I mean classical like states,
If I take any function P alpha comma alpha star, it will correspond to a physical, not necessarily classical but a physical state.
Any function you cannot take, I mean it should have certain properties, and for example if I integrate this over entire complex span it should give me 1, otherwise it will not be a distribution function.
It can be negative,
It can be negative.
but if it is negative,
Hmm.
then it would be like minus of alpha, diagonal element will be negative.
Yes.
It has to be compensated from somewhere else.
Yes. Yes.
Can be negative.
No, this P rho alpha it can be negative also. Yes.
It's probability distribution.
It is not probability distribution, that is the problem. Okay. It is probability like distribution. So, this is why we call it as quasi probability distribution. Okay. So, now you understand in quantum states of light, I mean generally quantum light, but there will be some light which are classical in nature in this sense. So, of course, one should be able to figure out expression for this given rho, okay, and this is I mean quite complicated expression which I will talk about it later. But this is again a function, real valued function which provides you kind of quasi probability distribution on phase space. Okay. The problem is that this can be negative for some values of alpha, this can be also singular for some values of alpha. Okay. So, therefore, I cannot call it as a probability distribution function. So, as
Like
not infinite, well it can be infinite, singular. So, therefore, it can be infinite
it can
also.
have poles.
It can have poles, yes, yes. There are other quasi probability distribution functions which are kind of well behaved. One of them is called Q function, or some people call it as Husimi Q function. Okay. So, Husimi Q function is, I will give you a systematic definition of all these distribution function later, but for the time being this Husimi Q function alpha alpha star is equal to this one alpha rho alpha by pi. So, that means you take the expectation value of your state with respect to a coherent state and then multiply by 1 upon pi, that will give you this function. Okay. So, what is it? Basically it tells you, so what is this one? This is the probability of finding the state your system which is prepared in state rho in this coherent state. If I can perform measurement in the coherent state basis, then this is proportional to the probability of finding my system in the coherent state, right. And this is what we do when we do what is called as heterodyne measurement. So, in heterodyne measurement, this is actually what we do, this sort of measurement in coherent state basis.
Coherent states are eigenstates of annihilation.
Yes, yes.
So, our observables are all Hermitian, we assume. The operators corresponding to the observables are always Hermitian, we assume. So, how do we measure this kind of things?
Yeah. So, coherence, when we talk about measurement in quantum theory, actually what is it that we do? Of course, you for your calculation purpose you need some observable, but when actually we do measurement, what is it that I do? I fix some measurement directions, like you put Stern-Gerlach along those directions, Stern-Gerlach detectors along those directions, right. So, it does not matter what observable you are going to measure, it is these measurement directions, those are important.
Stern-Gerlach experiment is for a spins.
No, spins fine, but you can extend it with higher dimension also. For coherent state, yes, this is bit tricky because this is uncountably infinite, but in principle I can do that. That is what this heterodyne measurement does, but the question is that for measurement per se, for quantum measurement per se, the role of observable is not that important. What is important is what are the measurement directions. So, which means the basis, this alpha coherent state basis. No, he is saying that coherent states are eigenstates of the operator A, annihilation operator, which is not Hermitian. So, how will you measure the coherent in the coherent state basis? Is that clear or no?
We will measure some observables, but some
think of even Stern-Gerlach. What is it that we are measuring? What observable we are measuring?
We have put a magnetic field.
Yes.
And it interacts with the electron.
Yes.
And separates the electron on the basis that if it has upspin or downspin.
Yes, yes, yes. So, what actually matters is in which direction you put your detectors, right. Does it matter whether you are measuring sigma z or some other observable? Does it matter? You put the magnetic field, inhomogeneous magnetic field along z direction, and then you accordingly put the detector, right. Okay, that is it. So, basically these directions of your detection will matter in your measurement, because that will give you the probabilities. Observables are secondary here. You can calculate average value of observable, etc., that is a separate issue, but for measurement setup in quantum theory, observable is secondary, is not it? Think about it, this is unfortunately our textbooks write in that way, that you fix an observable and all that. Ultimately, it matters in which direction you are measuring. Okay. So, this means that we perform measurement in the coherent state basis. So, which is basically heterodyne measurement, and the corresponding probability will be proportional to this, the Q function. You can also interpret in another way, because I said that this alpha is the this is the amplitude quadrature, this is the phase quadrature by root 2. So, you can also say that look, if I perform the quadrature measurement like x and p corresponding quantum mechanical versions, of course, they satisfy this I, etc., that is fine. if I perform the quadrature measurement, these are non-commuting observables, I cannot have joint sharp measured values of the x and p, but if I can manage to have some amount of unsharpness there, right. So, I blur their values, I am not calling x, I am calling it x in some region, similarly p in some region, then I can also say that this value corresponds to joint probability of having unsharp x and p values. Is that okay? And this tells you, and in fact, we can show that unsharpness, how much unsharpness I can allow. So, this is the minimal unsharpness I can allow, because that is guided by the uncertainty rule. Okay. Okay, good. And you can see that this q is always greater than equal to 0, right, because this is expectation value, and q of rho alpha, and also this is less than equal to 1 upon pi, is that correct? Because this value can be maximum 1, so this is less than equal to 1 upon pi. So, this q is a bounded function. Moreover, if you integrate it should give you 1. Oh, not 1 upon pi, I think it should be just pi. Okay. This should give you 1. Okay. So, this tells you that this is actually a probability distribution function, is not it? Because this is non-negative and it is bounded, and if you integrate, it will give you 1. So, this is a kind of probability distribution function, right. So, why we should not be happy with such a function, it is actually a probability distribution function.
But because if we know this, how will you write the state? Is it easy to write the state? Because
good question. Yes.
you can't just do alpha alpha like that.
Yes. Yes. Because we need to have this one-to-one correspondence between distribution function, phase space distribution function, and your state. Well, there are ways of writing this thing, but this does not, this is not a good function. Why? What about the classical or non-classical nature of your state? It does not capture, because this is everywhere non-negative, this is bounded. So, it does not capture that. Okay. So, in one way you can get rid of all those negative values, singularities, etc., by introducing this function, which is okay, but on the other hand you miss out all the details about the non-classical nature of your state. This does not distinguish whether your rho is classical or non-classical. Okay. So, one of these, I do not remember which one. So, this corresponds to rho having, I think it is anti-normal ordering, maybe the opposite will be true. So, anti-normal ordering means you can write rho as a like n and m is equal to 0 to infinity, some rho n m. What is anti-normal? First a, then a dagger, right? Yes, first a, then a dagger. So, a to the power n, a dagger to the power m, something like this. So, this is the, I think from here you get this q, maybe the opposite. For p, what is got is normal ordering. So, rho is equal to n m is equal to 0 to infinity, rho prime n m, this is a dagger to the power n, a to the power m. Okay. So, this is a coefficient, these are the coefficients. No, see, this is an operator. You can write every operator of your system can be written in this way. I mean, in terms of powers of A and A dagger, that you can always write.
Is it rho m n?
NM, sorry, NM. This is a coefficient, okay.
What did you mean by anti-normal ordering and normal ordering for?
So, any operator of your system can be written as sum of products of powers of A and A dagger, right. So, this is one such expression which is anti-normal ordering. Same operator can also be written in the normal ordering form, okay, right. So, this P distribution you can get the form of this P distribution for given rho starting from its normal ordering. Similarly, you can get this Q distribution function for rho starting from its anti normal ordering, maybe vice versa. I mean, I do not exactly remember.
Function connection between this
Yeah, of course. I mean, in principle you can, in principle what you can do, you can use this commutation relation, right. A dagger is equal to 1. You can use it to bring this into this anti normal ordering and vice versa.
No, but I am saying this P function.
Yes.
This rho prime n m.
Yes.
There is some.
There will be connection, there will be connection, yes, there is connection. So, my point is every phase space distribution function of your state is related to one such ordering. P distribution is related to normal ordering, Q distribution is related to anti normal ordering. There is also another ordering which is called symmetric ordering. So, in symmetric ordering you do not give any preference to powers of A or A dagger. Okay. So, for example, if I want to have a symmetrically ordered, let us say A square and A dagger. So, a symmetric ordering of this, how will I write it? I will write it like, what should I write? This is A dagger, A, okay, and then A square A dagger plus A dagger A square 1/3 of this. This if I do not look at, this is your anti-normal ordering, okay, right, and this is your normal ordering. Symmetric ordering means you should take all possible combinations. Okay. So, I mean that is why I said that you should not give any preference. So, such a symmetric ordering, this gives rise to what is known as Wigner distribution function. Historically, it is this Wigner distribution function which came first, and later this Q function, P function, all of them came. Wigner distribution function is a very well behaved function. It can be negative, but at the same time it is bounded. So, it can capture non-classical behavior because it is negative, and at the same time this is a well behaved function unlike the P function. Okay. In quantum optics or even in continuous variable quantum information, we will require also some other phase space distribution function. So, these are two extremes, anti-normal, normal, and in between symmetric ordering. There is also something called S ordered quasi probability distribution function. which is generalization of all these three ordering. Okay. So, basically which gives some preference to powers of A and remaining preference to powers of A dagger and all those things, and that preference is governed by this A's value. Okay. So, I will talk about all these things in great details later. What I just wanted to tell you is that so this is what will correspond to. So, understanding this P distribution will tell us the character of the state of light, whether it is classical, non-classical, etc. And one very important thing is that so P rho alpha star greater than equal to 0 for all alpha. I mean, when I say for alpha means alpha star also. This is equivalent to saying that rho is classical. Okay. In other words, if there is a violation of this condition, then the state will behave non-classically. In which respect it will behave non-classically? How do I understand this is non-classical? Of course, from mathematical expression I understand this is non-classical, because then this is not a proper probability distribution function. Okay. But there are operational ways of understanding this non-classicality. Operational ways means I produce my system in such state, which is state of light, and then I put photo detectors there. I look at how many photons are coming within a small time interval in my detector, and I look at the photon number statistics. Okay. So, like whether what is the probability of getting no photon, what is the probability of getting one photon, what is the probability of getting two photons, etc. So, I look at the photon number statistics. By looking at the photon number statistics, I should be able to figure out whether the state is classical or non-classical. Okay. In other words, the photon number statistics will tell me, will specify, in other words, this function, this P distribution function. Okay. So, whatever non-classical feature I can get to see with my state of light, it should be reflected entirely in terms of this P distribution function. No other distribution function can capture all these properties. Only this P distribution function can capture. Unfortunately, this is not a well behaved function in general, but there are plenty of operational ways of identifying non-classicality in a state rho, plenty of ways. All of them can be captured through properties of P distribution function, all of them. Okay. So, this is very crucial. So, as a result, if I know P distribution function, I know everything about the classical or non-classical behavior.
So just the fact that just through the fact that P distribution function is negative,
yes,
any operational non-classicality can be captured by the negativity of P distribution.
Yes. So, P distribution function for a state being negative means negative, it cannot be negative everywhere for some values. So, it means that the corresponding state has to have a non-classical feature. How will it be reflected operationally? That means, in terms of photon number statistics, that one will have to design, but in principle this is the case.
And what is the situation with Wigner distribution?
Wigner distribution negativity means it is non-classical, of course,
Okay,
but other way it is not true. Like squeezed vacuum state, Wigner distribution is Gaussian, therefore, it is everywhere non negative, but we know that squeezed vacuum state is non classical. Okay. So, let me try to understand a little more details why we consider these coherent state basis, okay, in order to compare with the classical light. So, if I look at, so this we discussed last time also, the wave equation for electromagnetic field in, I mean, so this is 1 upon c square del square del t square E of r t is equal to 0, right. This is the standard wave equation, right. Now, as a solution of this, what I can do, this is the basically your fixed, I mean this is the scales with the energy, or yeah. So, let me write it like these are dimensionless amplitudes, then this is twice pi I in t plus alpha star, this is r t e to the power minus twice pi I nu t. So, this nu is your frequency, oscillation frequency, you can think of this that twice pi nu is equal to omega, this is the angular frequency, okay. And this angular frequency, you know how is it connected with the wavelength of your wave, okay. So, this is for a particular mode, so one frequency. Now, this is constant, of course, this. Now, these are dimensionless amplitudes. So, this you can take it like some magnitude, and this is phase. So, for plane wave we know what will be this form of this phase, for spherical wave we know what will be the form of this thing. So, all these things we know, for Gaussian wave also we know. Okay. Now, let us so let us try to write it, this is in sine and cosine. So, what will be this one? If I write it in sine plus
this will be sine cos 2 pi nu t.
Yeah. So, this is so this will be let me call it as x of r t cosine 2 pi nu t plus or maybe I should put it, okay, let me see, this is p r t sine 2 pi nu t. So, this is, you can think of these as, this is what, alpha of r t plus alpha star of r t. So, real part of alpha, right, and p of r t is equal to alpha of r t minus alpha star of r t. Is that correct?
Some I is missing somewhere.
Maybe I of this, is that correct?
Yes, I think.
Yeah, I think it is correct, yes. Okay, yeah. So, this is imaginary part, you can say. I mean, ideally one should any. So, what is it? So, basically you see that you can write this single mode electromagnetic field with these components. So, this is the cosine component and this is the sine component. Okay. So, these are called, so this is basically amplitude quadrature and this is your phase quadrature. Right. In fact, I am sure you must have learned this phasor diagram, in wave optics. Okay. So, where this any wave can be represented in terms of these two components x and p in the phasor diagram. Okay. So, what I can do is I can think of. So, this is basically you have your p and this is your x, right. So, a particular one will have these components, this is twice pi nu t, okay, depending upon this cosine and sine, right. So, a generic one I can write it, generic quadrature I can write it as x cos theta plus p sin theta, right, where theta is this angle. So, this is a generic quadrature, right. Okay. Okay, good. So, in the quantum version of this formalism, what is it that we have done? So, basically we have made this to be an operator and this to be an operator. Of course, I should be careful about that commutation relation, whether it should be so. So, that one will have to be careful, and this corresponds to your A, okay, the annihilation operator, and this corresponds to A dagger when you quantize it. Okay. These are the field amplitudes. When you go to quantum version, these are the annihilation and creation operators. Okay. So, if I now write down, there is an issue with this. I think I should have written it like square root of 2, then things will be much easier. Okay. So, then what you need to have is, how will I change it here? This should be the case, right. I mean, because why I need to do that, because I need this thing, corresponding operator should have. So, I take h cut is equal to 1, this should be iota, otherwise it will be twice iota. Okay. Okay, good. So, this is a generic quadrature operator corresponding to this angle theta in your quadrature plane. So, now if I look at the in other words, you see that this x, it should correspond to A plus A dagger by root 2, right, and this p should correspond to A dagger minus A by root 2, I think so. Okay. I think so, right, you can verify this. So, now if I now look at, let us now take a number state, Fock state. Okay. So, if I now look at the expectation value of this operator, what is this? This is cosine theta in x n plus sin theta in p n. This is my Fock state, right. And what will be this? Because of this relation, this is 0, right. So, in the number state, the average value of this quadrature, and it does not matter, this is for all theta, the average value of this quadrature is 0. On the other hand, number state means you can think of is like in the classical domain, it is like intensity of light. Okay. How many photons are there means basically intensity. So, if I look at this this quadrature value, this is classically, this is what you will obtain, given some light which is given intensity, I mean you will get a value of this, right, but this is theta dependent. On the other hand, for number state this is 0, right. Okay. So, you see that number states in this respect are quite different from classical states of light. But if you follow the same procedure with coherent states, okay, so then you will see that for coherent state what will you get? You will get cosine theta alpha x alpha plus sine theta alpha p alpha. And now with this rule, what will be this value? This is 1 upon root 2 cosine theta. What will be this one? This is alpha for this, and for this one this is alpha star, I guess, right, plus sine theta, this is I, and then it is alpha star minus alpha, okay, right. I mean, you just calculate this one with, that A acting on alpha is equal to alpha alpha. So, this you will have to use. So, therefore, what you see is that this is 1 upon root 2 twice real part of alpha. So, this is basically square root of, this is cosine theta, and this is minus I. So, this is plus root 2 imaginary part of alpha sine theta. So, this is theta dependent, right. So, now so basically it tells you that with respect to a coherent state, if I look at the average value of this quadrature variable, quadrature observable, it is a theta dependent, and you may think of it like, you are adding the x and y components, okay, it is a projection. Okay. So, my point is that with respect to coherent states, if I look at this quadrature observable, its average value, it kind of resembles the so it captures this fact that you have this angle theta here, okay, unlike this case. So, in other words, this average quadrature observable with respect to coherent states, it is in fact one more thing we can show that, if I look at this theta square with respect to alpha, this will be also very small, okay, right. So, in other words, coherent states are somewhat close to, and this quadrature, the classical correspondence of this is this variable, what I have written here, this variable, this one where you replace this by theta. Okay. So, the coherent states in this sense, it resembles your classical electromagnetic field, okay, because it reproduces, because this you can take at your wish, that this is my expectation value of my observable with respect to alpha, or you can take this as your value of the quadrature variable x theta, this is also fine. So, point is that with respect to this average value of the quadrature variable in terms of coherent states, they are matching. So, this you can think of as your value of the quadrature variable x theta, because this is up to me. Okay. So, therefore, you see that with respect to coherent states, these average values of your quadrature variable, they are matching. In this sense, you can say that coherent states behave very closely to your classical, I mean states of classical light. Its uncertainty is also very small, I mean this is the minimum, and the the average value matches with this, unlike in the case of number states. Okay. So, there are other features also which perhaps we will discuss later. So, keeping all these things in mind, the coherent state basis is the ideal basis for dealing with um, for to deal with comparison between classical states of light and quantum states of light. Okay. Right. So, this is why we need this diagonal representation, and thereafter also the phase space distribution function, that is fine. Why we need other distribution function, that I told you, because the p distribution is not well behaved. So, we need other distribution functions. Okay. So, so what we discussed today is basically the the relevance of coherent state basis in order to discuss the classical and non-classical nature of light. Okay. I mean, light means continuous variable, I mean states of continuous variable system, not necessarily light. Okay. Okay. So, this is what we discussed, and then what next time what I will do is I will go in details about the the connection between the different ordering and the phase space distribution functions, and that will eventually lead us to this Glauber-Sudarshan p distribution function. Okay. Is that fine? Good. So, any question? So, maybe I should tell you some of the so one thing which I will follow, maybe not entirely, is there is there are two you can say review articles by Cahill and Glauber. So, this I have not followed so far in our discussion, but this is a, I will have to remember, this is somewhere in 70s. There are two papers, okay, one after another. One is about this ordering, these normal, anti-normal, etc. The other one is about these Weil representations of operators, okay, and these two are very important in our phase space distribution function description. So, this is somewhere during 1970s.
Is it ordered expansion in boson amplitude operators?
Exactly, one paper is this, there is another one.
Density operators and quasi probability.
Yes, yes, in 77 or something like that, right? Yeah. Yeah. So, I will follow that to some extent, and then of course, there are plenty of quantum optics book that you can look at, and later on of course, there are review articles on continuous variable quantum information that I will follow. But for our understanding of the the technique, these papers are very, very important. Okay.
Once again, like the discussion we had in the last part, this x theta.
Yeah, so, what I said is that if I take number state, then these quadrature operators in some angle, it does not matter what angle you take, the average value of quadrature, corresponding quadrature observable with respect to number state does not capture it, because it is independent of theta. On the other hand, if I take the average value with respect to coherent state, it captures, because this I can always call it as it is the classical value of the quadrature observable, because this captures, because it is theta dependent also. So, in fact, one can go one step further, you can look at the variances also, you also match. So, basic point is that in what direction you are taking your quadrature variable, number state is inert to that, whereas coherent state is actually matching with that. Okay. In fact, in this sense number states are very, very non-classical, okay, except the ground state.
But this does not quantify for you the number of photons. This quantifies for you maybe the intensity of the light, right?
Yeah, for classical light we only look at intensity of light, number of photon. In classical light it is actually the intensity.
Okay, so you're trying to capture the classical behavior. Okay.
Okay. Yeah, because classical light I cannot talk about photons, so I only talk about the intensity. In fact,
I thought this expectation value, like you're taking expectation values to quantify how many photons are in that.
well, basically the intensity in the case of, so basically you can look at A dagger A also. So, this is either with respect to number operator or with respect to the, so again if you take with respect to number operator, this is n independent of theta, but if you take coherent states it will be theta dependent. I mean theta dependent means it will have information about the quadrature. I mean for coherent, so this is n for number state, whereas if you take it for coherent state this is mod alpha square. So, this is your intensity. Okay. So, it actually captures the classical nature of light, whereas this does not. Okay. So, these are two extreme cases. So, you will have states in between these, okay, plenty of states.